Welcome to today's webinar. The topic today is economic optimization of structural components in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, technical content of the website, German and English webinars, newsletters, and so on. I will be the moderator today and I will answer your questions. The presentation will be done by my colleague Florian Hiddemann. He's a product manager in our company, and he is, for example, the main responsible person for the optimization add-on. Okay, then I say some words how you can ask questions. First, I switch off my camera that you can see the full screen. You can press that button, then enter your question here, press send, and then I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that should be all from my side. I hand over to Florian. Florian, it's your turn.
Yes, thank you, Andreas. Today I want to show you how to optimize your RFEM models with global parameters and our add-on Optimisation. Especially today there is part of the presentation a new algorithm we developed, which has some advantages I like to show you later on for specific models. But first, I assume for this webinar that you didn't have any contact with optimization or global parameters in RFEM at all. So we start with a very easy tutorial example. It's just a simple cantilever where we have also here, in addition to the full load bearing here on the left side, there is a nodal support, and we will model the position of the nodal support in dependency of the beam length for the first. It's very easy. It's very easy to follow. So you can check the principle how the add-on optimization is working and what we like to optimize. You can see here we want to have a model where the minimal displacement, overall the beam length, will appear. So for that, we switch to RFEM and start with the first model. Later on, we will have two models with a practical example as well. But first, we start with a simple cantilever to demonstrate how the optimization is working. And now, to start, we need something to optimize. For this reason, I will define a node somewhere on the beam. It doesn't matter what we put here as a value for beginning. So now we have here a node on member. And to optimize, we need a global parameter or some other parameters. Later on, we will get to know some other parameters. And now we call this position nodal support. We can also define a symbol here. And since we want to define a percentage, we have to look for the right category of unit group. So let me just see relative length, right, exactly. So let's define 40% as a start. So we have now our global parameter, accepting with OK. And now we go to the model and use this global parameter to define the position for the nodal support from the start. We can select we just clicked here on this arrow, on this black arrow, and think about it. Every field which has this arrow, you can use global parameters in your model. So it's a very flexible system. And now we choose this position X, click OK and insert, and now you can see we are using this global parameter for this value in this input field. So as you can see here, the node moved, and we will define a nodal support on this point now. So we want to show how the influence of this position is affecting the overall displacement from the beam. There's only self-weight activated. It's a very, very simple model. We have just load case 1, active self-weight. And if I calculate the model now, nothing special is happening. We will see a normal calculation where we can have a look on the displacements here at the beam end. Now we want to optimize, and we will do it from scratch. So we go to the base data, and if you have this add-on optimization and cost and estimation of CO2 emissions, we will see how this works later on. You can activate it, and now you have some new features in your model. We go back to the global parameters, and now we can see here on the right, maybe you had a look on this in the first step as well, these optimization parameters are available if you choose to the definition type for the global parameter, switch to optimization. The red color is indicating that some informations now are missing. And you can define it here now on the right side. For this example, we want to try to go from 10 to 90% the beam length. And you can now either define the steps which are done in between those min-max values or the increment. RFEM will figure out what is necessary. So if you, for example, say let's make 100 steps, you will go 0.8 as an increment. If you say we go 1% at a time, we have 80 steps from 10 to 90. Including the start and the end point, we have now 81 possible positions for this nodal support. The value stays at 40%, so the model won't change now. Now, if we want to calculate again, we will see nothing is changing. RFEM still has results, has a self-weight. So now is the question, how do we get to optimize for a minimum displacement? You can reach this over optimization settings in the menu Calculate, or go to the Navigator Data, where you can find it under load cases and combinations. And here you have all optimization settings you have defined. I go over the menu here, and we see we can now make some adjustments. For this demonstration, we want to use all possible values to show. So it figured out from the global parameters and all other parameters which you can optimize. We have 81 states, and therefore it's the only parameter we have in the model. All possible mutations. So this is a number of possible variants is 81. And for this easy example, we want to calculate all of these. So we want to calculate 81 optimization mutations, and the target value you can define here is the minimal vectorial displacement in the whole model. You could also choose the minimum member deformation here, but for this example, it doesn't matter if we choose the vectorial displacement. So I will accept and OK. And now if you're expecting the add-on optimization to step in, don't worry, we have to do another step. So this is because we now just have defined what we want to optimize, but we didn't make it ready for use. This is a very important thing. You have to click on active here. It's kind of like a safety mechanism, because this takes time to calculate. We will have in the real world a lot of mutations here to calculate, and therefore after each optimization cycle, or if you didn't do it in the first place, you have to activate this checkbox, and then the next calculation will include the add-on optimization. So now if we accept here with OK and calculate all, the optimization will start. Or I can just apply or say OK. And now the next calculation cycle will start optimization. So we have only the load case. We have no design checks in place. It's just a static analysis we are doing here. And now you can see what is happening. RFEM performs one model after another and just calculates with all possible variations for the global parameter. RFEM saves then the target value and the model name, which included which parameters was input for the calculation. The results are not stored here in this way. That would be too much data. Only the last model, which is found as optimal, after this optimization run through, will have the results in the last steps. But you can change to any model after the calculation and calculate it again. So now you're seeing it's kind of boring. You might think we are now stepping from left to right. It's like a loading screen here. And we won't wait until we reach the 90%. I am prepared for this, so we have time to watch the results together. You can cancel this calculation at any time, and don't worry. The results or the models which are calculated so far will be there. So now at this time we have calculated 12 models, and you see those optimization results. The best is at the time here with a position of 21% from the beam length with 18.6 millimeter deformation. And I will jump to a prepared model which has the results stored. You can see now here are all 81 models calculated. I set up in the optimization settings to keep all 81 models. Yeah, this number defines how many of the best models are saved for later use. And we can see at some point it's not getting better to move the nodal support to the right. I think most of you have foreseen that. And we have an optimum at 72% with 0.2 maximum deflection. So let's jump back to our presentation. This was just a quick tutorial to demonstrate how the add-on is working. But for the praxis, we want to have some more optimization goals and some complicated stuff to do. Because in reality, maybe there are a lot of effects on your model and you can't say which is the best from the beginning. You want to try out with a lot of parameters for different goals. What can we do with this? In the target value, you have seen it before, we have several things to choose from. So for example, minimum cost or minimum CO2 or the minimum total weight of your static system. And what is important to take care of? You have to think the results of each calculation are evaluated against after the calculation only for this set up target value. So be careful what you are choosing here and what you define in the model. RFEM will just evaluate after this single target value what is the best model for you. Every calculation which is done, it's with a complete set of individual parameters, and RFEM performs a complete calculation for each run. It will, at the end, like you have seen before, provide a comparison of the n best results, which you choose from, for the standard default value, is it 20 best models are kept. And what is very important to know, and really is a strong argument to use this optimization add-on, if you use this optimization together with dimensioning add-ons, like for timber construction, concrete or steel design, or even stress-strain analysis with limits you defined, only successful results are kept for the comparison at the end. So if you have a calculation which includes errors or not appropriate design checks, it won't go into the comparison at the end. We will see this in our examples, but this is something important to have in mind if you work with optimization. Maybe you thought already about the challenges. In our simple starting model, it's only 81 models. Takes a few minutes to calculate it, depending on the complexity of the system. If you have a more complex situation or a big 3D model, even the 81 models take some time. So in practice, you can see here, this is from our example. We will have a look later on. There are some values to optimize. And if you multiplicate each different state for each parameter, as you see here, two geometrical parameters and also some cross-sections. And if you multiply them, you will get over 500,000 possible mutations. So if you want to calculate all of them, like we have done in the simple tutorial example, with today's hardware, you will have a hard time to find what you are really looking for. Because each mutation is to be analyzed in full. The calculation is like you do in a single time with RFEM today. But don't worry, we have a solution for that. You can combine it with a clever strategy, which is useful to find very fast the best capable parameter sets to achieve your optimized target value. We have two algorithms now for you here. One of it is a particle swarm. It's already implemented for quite some time. And the new one, the ant colony, is featured later on in this webinar here. And now you can make use of this clever algorithm. It will try to find the best models out of these big mutations with only calculating 1 or 2 or 5% of them. You can choose how many should be calculated, and we will have a look on this in the examples. So this is a big advantage. We make parameter studies based on our global parameters and other optimized values, and use clever algorithms to find best parameter sets as fast as possible. So what do we have a look on today? I have two models brought here for you. On the left side, it's a beam with a supporting structure. Here, it's a timber construction, just a parametric cross-section. And here is a truss geometry, which is flexible, designable with global parameters. For this model, we will try to find the minimal cost of this construction element. On the right side, we have a steel frame with a suspended beam. This model here is very good to show the new advantages for our new algorithm ant colony, because the ant colony is quite strong to find profile cross-sections. I will show you later on in some theory why this is the case. Also, there is some geometrical variation here, and I try to make a system which is not easy to see what its best with a look on the first glance, because these points here of the suspension are also movable, and we will find an optimum for this beam here. It could be in a event hall or other usage. It's just for the design, for the first design here as an example, when you are trying to optimize elements of your structural model. So we start and have a look with the model on the left side. We go to the beam with supporting structure. So as you can see here, I will give you a quick overview for this model. In reality, you can, of course, use the optimization model with your whole 3D model, which includes every effect you want to have. And think about it, global parameters can be used in a very flexible way. Here for this model to demonstrate the effect, I try to make it easy. And we have here a 3D model, and I added some spring stiffnesses here as nodal supports to simulate 3D stiffness elements, which you would have in a real world example, so that we can here have a look on the isolated effects of the load bearing system, of the load bearing. So, all right, let's switch to the parameters. For the first, we will ignore that everyone is red. I have here some parameters defined, and we have the height of this beam as one parameter. And then here you'll see Z and X coordinates. These coordinates represent these points here from this truss geometry. So we have a very flexible way to edit it. I can demonstrate it. You can, with those parameters, manipulate the height and also the position in over the length. Both nodes will move here. There are nodes on this member. There is a normal node, and with this system we have kind of a lot of flexibility, which has a big effect on the load bearing capacity of the system. So I will go back to the initial values. And our optimization goal will be the less cost for this whole construction. RFEM should try to find the best geometry and the best beam height for this load setting here. I just made up here two exclusive load cases. They won't come into account together. They are in a design situation, and we have here defined all the four standard design situations. I use the German national appendix here for demonstration purpose. And you see it's very easy. It's a self-weight, it's a traffic load, and it's combined in a very easy way. We have self-weight and 1.5 for the second load case, self-weight and 1.5 for the third load case, but not those ones together. Why? This is because it's not symmetric here and kind of an interesting structure. And maybe you already have an idea what should be a good result here. But we want to use our add-on to find a clever situation also from an engineering point of view. And let's see how we can achieve it. Like in the tutorial, we will set up this from scratch. So already designed, already set it up. Here is the steel design and the timber design. And now we go also with the optimization add-on. So now it's activated and I can make some optimization settings. For this example, we have some geometrical states here. You see it on the right side. Now the values to optimize are the beam height and these 5 states of the z coordinates and these states for the x coordinates. And even that are not, it's not as much here. It's only 3 to 5 states, but if you multiply them, already over 28,000 possible configurations for all those parameters. You won't have a chance to calculate them all unless you want to have a special laptop and take some time for this. So what do? First, we will make use of the particle swarm and just calculate 2% of all these possible mutations. We will keep the 20 best ones. And like said before, we want to have the minimal cost. We will set this as active. Let's make it later on. Let me show you some other things first. But these are our optimization settings we will use in the calculation. You have to do something more now, because RFEM doesn't know how many or how much all these materials and cross sections are costing or costs. So we will use the way to define it over the materials. And if you have the add-on activated, you can go to a special menu, which is now available for you in the materials, for example. You can see here we have 3 new checkboxes, and these come from the add-on optimization. As a default, the estimation of CO2 emissions activated, and now you have here a new register. We will now add the cost estimation and see what is what sits behind. If you go to this register, you can now define for every member, surface or solid of this material your own cost values. So for this example, I go with some example numbers I have chosen, and I will say every member will cost 1,500 euro per ton for S355. S355 are our tension bars here in the truss frame construction. And you can also see the consequences here. We have this amount of members here in the system, and therefore the costs which are estimated are around about 20 euros. If we go to the timber beam here, it's from C24. I say it will not be defined by the weight, it will be defined by the volume, and therefore we say it's 500 euro. Oops, I have to switch to the cost estimation. So we will define the cost estimation by the volume, and it's 500 euro per cubic meter. Yeah, and you can see the influence of the cost will be a lot more than for the steel construction here in this example. Now we have 400 euro by the timber beam, which adds in total together with the S355 to 420 euro. And the last material which is used here, it's these are these members here. They are made from S235. And we will do it like for the other steel sort. We will define it by weight with 1,000 euro per ton. So it takes part with 16 euro, and now in total our construction cost in this example 437 euro. So how is the model working? I will show you. As you might recognize, the length of these members goes only through the timber. And let me show how we have done this. For the first, how the global parameters are used. I go to the node at the end of this member here, and we can see I set it up global coordinates. So here x1 is used. You can also see it in the formula. And for the z coordinate, I have used z1 and half of the beam height. This is because I only want to have this length here represented with the global parameter, and defined an eccentric situation to take the correct beam length and material amount takes the correct material length into account. So of an eccentricity, I defined axial offset from the adjoining members. And as you can see here, if you activate this checkbox, the member doesn't go to the crossing lines of the system lines. It will only reach to the downside in this example from the timber construction beam here. Okay, I also done it with the tension bars, and so we have quite a nice system where the system lines are crossing in one point, but the materials are as you might see it in the real structure later on. Okay, so now we should have everything to calculate, and let's see if it's unchecked. Yes, for the first we start with a normal calculation, no optimization yet, to have a look what are the results, because now we have some design add-ons in place which make, as you already know it, your design checks. And what is important to recognize, this model would be part of the later on comparison from the add-on optimization, because all design checks are fulfilled. If you would have any model which doesn't have a successful calculation, it would not be part of this comparison at the end. So the add-on acts like kind of a filter for your models and throws out the garbage which wouldn't hold up in reality. So we change it now. I made a very low trust framework now, and let's see if the calculation is still working. So we can have a look here in the overview. Yes, for this example, for this load it would work. And if we change the beam height now to 0.3, we should see that this construction now doesn't fulfill all the design checks which are activated here. So we have a problem with the tension in this tension bar here, serviceability state, and also with stability in the weak axis, which is between those points here. Okay, this model would not be part in the end in the comparison of the add-on. So let's have a look how this is working in action. I will now activate it. We have a minimal cost particle swarm and calculate all models. And let's have a look for the first iterations. As you can see, 2% of all the possible mutations are here over 560. And RFEM now calculates at the first with a random variation of those parameter sets and is trying to find models where all design checks are fulfilled. So as you can see here, we perform some calculations, and it's already optimizing. It will now calculate and value every single model which has fulfilled design checks with the target costs, and the particle swarm algorithm tries to find geometrical states of parameters where it, from a statistic point of view, expect low costs. So as you can see here, you have quite a big variation of costs already. And if you would calculate it all the way down, you will have some more models. As you might expect, I already have done this before this webinar. And as a personal tip, when you can, how to work with this add-on here, you can make it in the afternoon if you're leaving the office and your computer isn't used anymore. Just start a calculation, and overnight you will have a lot of results calculated, or over the weekend. This is quite a nice time to do this. And of course, what's another option? I want to make some I want to bring this near to you. You can also calculate in cloud. This is a service we offer as well. You can go to our sales and ask how this is done, and then you can also calculate your models, which are which takes a lot of time in the cloud computing. So now we see the results here from my prepared model, and as you can see here in the graphic, it looks quite clever, because we have here our two load combinations which are important for the system. And as you might see it from an engineering point of view, this construction here follows the bending moment distribution quite well. And all the results here in the lower table are very, very close by. So this is a sign that you already reached some kind of global minimum, because you can see the beam height is in every one of the best 20 models 35. This is a good sign. This seems to be a good reasonable beam height, and the parameters here are also quite close to each other. So the model figured out that these parameter sets are very good for what we are trying to achieve. And if you remember, the first models we had was over 500 euro. These are about 380 euro. We already optimized our construction element in a cost-effective way. So this is a first example. Of course, you can have a look on all the other systems, but you will use results you have calculated with the add-ons. But that's no problem. You can calculate the results at any given point from each model here again. I'm just clicking through with double click, and you can see the systems here are quite similar. If you go back to the best model here, let's calculate the results again. If you have a bigger model, I would suggest you save with results after an optimization run, so that you have those results here also stored if you calculate it overnight. And we have a look on the design overview. With this setting here, the program found it's from 97% to 81%, from steel design and timber design add-on. These are quite effective usages of your materials and construction. And yes, for the first example, we make a point and switch back to our presentation. So you have seen the principle here now on a practical example with the beam supporting structure, and we had as global parameters more or less only geometric values. And now we switch back to the steel frame with suspended beams. This is more interesting here for the ant colony algorithm because it's including the task to find optimal cross sections for some profiles here. We want to have as a target value the minimal weight of one frame and jump into this model as well. So I used a very a close approach to the other model. I only modeled here a 2D frame and defined here some spring stiffnesses in the out of plane direction to hold the model and to stabilize it from a numerical point of view. This is simulating what you would have in a real construction as your three-dimensional stiffness for the system. So here's enough to have a look from the side for this easy example. The approach here is to find a good system in an early design stage, and you have a lot of options. Which profile are you choosing? Which geometry you are choosing? Depending on your boundary conditions. And therefore I set it up a very easy load setup for demonstration purposes here. We have some self-weight on the frame itself and also on this beam construction here, which is connected via tension bars to the steel frame itself. We have also example wind loads and some snow. And for this easy model here, I only have defined a design situation for ultimate limit state with those three load combinations to have something to play around with different distributions of your member loads. Okay, so let's have a quick look. How the model is parameter how the model can vary parameters. So we have here two global parameters for geometry. One is here for this curve, the length of the curve, and one is here for the position of the suspended beam. And if we change this, you can see it already on the right side. We will use it from 1 meter to 4 meter. I will show you how this affects your model. Now the suspension is very close to each other, which has quite an effect on the moment here for this beam in the roof, and it also has an effect on the moment distribution of this beam, which is underlying. If we go to the opposite, maybe you will go for a big moment here, and the load application on the frame is in the middle. It's now here also a different distribution for shear forces and moments. So it's quite interesting. There are two effects for this beam and for the frame, which are not predictable from the beginning. Which point here is effective for the whole construction if you see for the total weight of all components. Also, we can manipulate here the length of the curve. I go to 2 meters to demonstrate how this is working. And you can see here now it's longer, it's defined on this member. We have here defined with a global parameter in the section die Routenlänge, das ist the length of the curve, with this global parameter. So, but there is more to optimize in this example. Let's have a look on the cross sections. For this example, I want to know which combination, together with the geometric parameters, is the best for this beam end here and here on the cuff, and for the base steer frame here on the upper side. So this combination, both profiles will be optimized, and also this IPE profile here, which is connected via this suspension, via these hangers here. So how do we do this? This is something you have not seen yet, and we switch to the sections menu here. So let's edit our section. You can see here, these are our 5 sections defined in the model, and we want to optimize number 1, number 2, and the IPE profile here, number 6. For the columns, we let it with HEB 260 for this demonstration purpose, and the hangers here are R20. We won't tackle them. If you want to use the optimization add-on together with the sections, you will need to check this box here. But first, I forgot obviously to activate the add-on in this model. As you can see before, Steel Design is already activated. Now we activate optimization. Go back to our section menu, and now we can check optimization for this cross-section. We could also use cost estimation here, or estimation of CO2 emissions. You can define it as well here in the section. In the last example, we saw it defined by the material. This is then applied from materials. This is also an option. You can define the costs at a specific section you like to differentiate, or by the material. And for the reason we do not need this in this example, we deactivate both estimations for cost and CO2 and just run here the optimization box. What will happen after this? If you check this box here, the optimization parameter will try to find the best section in a series of some in a section series. So if you have here, for example, HEA profiles, you can select for the first any profile you want, and the optimization algorithm tries to find the best section from this series. So all of these sections here will be considered as a parameter for the model. So only the HEA is here important together with the material, and what special section of this series will be chosen is now the task of the optimization add-on. And we will check this here for the cuff, for the beam in the upper frame, not for the columns, not for R20, and we will do it as well for the IPE profile. We can here also deactivate cost and CO2 estimation. It doesn't matter if it's activated, but it's a little bit more cleaner to deactivate for me now. Okay, so this gives some parameters now. And as said before, in reality, your variance for the parameter sets are going big in a very short time. If you have some task like this, you have now 3 profiles from C series you want to optimize. And we go back to the settings here. And now you can see this is from the challenges from your PowerPoint presentation I showed before. These 3 sections here will sum up to over 500,000 possible combinations. And because of this, here are that we are using sections as a discrete parameter, where are no values in between of 2 alternatives. The end colony is the approach you want to choose for this, because this algorithm is very strong to find for those problems here the best solution. In the end of this webinar, we will look on the theory behind. So let me check if something is missing. So we start another calculation again, and you can see if you calculate 2% of all those combinations, you have 10,160. This is something maybe you want to calculate overnight or at another time. And as you can see here in the background, RFEM now tries to play with the parameters as well, and also with the profiles. So the variation of the target value now is quite big. We have here now, at first, if you combine in a very brutal way those profiles, maybe your engineering heart is bleeding now if you see those combinations. But trust the process. The more models are calculated, the end colony is getting better and better to find clever and useful combinations for those parameters. You can see here, the program now, besides of the geometric parameters, is trying to choose section profiles from the series that fulfills all the design checks which are used by the add-on steel design. So obviously we won't wait for the next 100 or 1,000 combinations here. And this is the same like the models before. I prepared this with the calculation overnight. And we can see the first approaches here are about 4 to 5 tons for the weight of the construction. And now we go directly to the results. This is the prepared model, and here it's looking a little bit different. This looks quite neat and slick, and we have 1.8 tons of optimization here. And the program has chosen that an IPE 100 together with those profile and the geometry here of the cuff length, and this position of the hangers is a clever way to tackle this problem. And we can have a look on the moment distribution here, because the program have tried out a lot of parameters also with the geometry and all cross-section proofs here. Maybe we have a solution an engineer manually would take some time to try out and check every detail and checks every combination. So if you might know what profile series you want to use, but you have a little bit to play with some details in your construction, this can be a very effective way to save money in form of steel weight here in this example. So you can see this length of the cuff seems to be very nice for the system, and also the 3 meters for this hanger point here seems to be a good approach to find a compromise between the usage here from this beam and the usage for the steel frame. We're looking in the design overview. What we have here, we are about 90% usage, and in some other calculations I have done before, this point here has sometimes stability problems when you choose a wrong cuff together with wrong settings here for the load entry points. So let's also have a look on the parameters here. You can see it's not the maximum parameter. This value, which is found as optimal, lies in between the min and max value. Again, this is a good sign if your parameters would reach all the max value or reach a minimum value, this could mean that you have to increase your max or min values because your optimized system could lay outside your defined max or min parameters. But for this model here, 3 is between 1 and 4, and 2.25 is also between those values. So yeah, from an engineering point of view, this add-on has found a clever system with a much cheaper solution than the 5-ton steel in the random calculation before. Why the ant colony is so suitable for this kind of problems. We're now getting in the last minutes of the webinar. I would like to point out this new feature because with the particle swarm we already had for this add-on, it would not be so efficient to find the best optimum within the short calculation time. The ant colony has some advantages. It is very, very suitable for the use of discrete parameters, such as cross-sections of a profile series. A discrete parameter is, there are some values which doesn't have any values in between, like if you have geometry or some percentages values where you can see, like in the first example, the optimum is about 72%, and a bad solution is around 0.3 or 30%. Then the particle swarm can see, okay, I have to be close to 72%. With a discrete parameter, the algorithm can't tell if it's better to have an IP600 or IP80 because those are only random section names for such a mathematical algorithm. And these ants here, these are search agents, have a special strategy to deal with it. Just to have this in mind, a rough introduction to the ant colony. You have in the first place your random search agents here, and in the first calculations you have seen it in the example as well. It's quite random which profiles are picked together. The ants are running through this possible selections for the profiles. And for example, this ant here chooses IP600 together with the HEB 1000 and a very small rectangular profile. And this is very random at the beginning. But each ant will get a result with a target value. And in a later stage, all the paths which have good target values compared to other ones will be reinforced with pheromones, like it is in nature. You know it, if there is a street with ants, they are reinforcing this path, and this increases the possibility that other ants, here search agents, will also take this path and be in the neighborhood of those paths. So if a profile series is ordered in the strength of the profile, the ants doesn't have a clue how much better a profile in the neighborhood is, but they will be around these parameters here. And good paths with good target values at the end will be reinforced, and therefore a lot of ants try to go here around and maybe also consider this profile or go this path here. And this is very clever. So you can reach a very good optimum of your system for this quite high number of combinations. With 3 profile series, you have seen it over 500,000, and you only need to calculate maybe 2,000, 3,000 of them to find a very good optimum for all of those known combinations. If an ant goes a random path here, like for example, with the high profiles, you will get a bad target value, and these pheromones will be removed from paths, so other ants won't likely to look here in this neighborhood. Yeah. This points out how our new ant colony gets to good results. I have shown you on our 2 practical examples. I hoped you enjoyed it from a very easy tutorial beginning now to some theory with clever ants and optimized results in practical systems. I hope that this inspires you how you can use global parameters, optimization, discrete parameters like profiles in your own models. And please have in mind that you can run it also in our cloud solution. So you don't have to worry to do other tasks with your local hardware in the meantime. It's only calculation time, and in the end, it's quite a nice addition to the design add-ons to optimize some structural elements for stiffness, or like we have seen here for costs and weight. And I hope you have enjoyed this webinar, and I would be happy to see you next time in a following series. So for this time, I would like to give back to Andreas and thank you for your attention. Have a nice day. Have a nice time. See you soon.
Thank you, Florian, for your presentation. I have an additional hint. Just use our free online services, such as the GeoZone tool. Only a few clicks are for free. If you need more clicks, you can buy a package for clicks for that tool. Then the cross-section properties or the FAQ and knowledge base with a lot of articles that will help by your work with Dlubal Software. And you can also download models from the website, also from today's webinars, for example. Okay. That should be also all from my side. Thank you for your attention. Thanks to Florian for this presentation. I wish all a nice rest of the day. Bye-bye.